Good morning, everyone. Happy Friday. Uh, how's everybody doing? Good? Yeah? Nice. Um, I'm assuming your blank vacant stares means good. Uh, I'm taking certain creative liberties there, but yeah. Uh, we're in the home stretch now. We only have 2 more weeks together, and then you'll be expert programmers who can go into the world and do anything that your heart desires, the tools that I've taught you. But we do have a couple of final interesting things to wrap up before the course is officially over. In particular, over the next week. So far in the course, the focus has been on just getting things done, right? Like so long as the script or the program worked, we were happy. We patted ourselves on the back and called it a day, right? And when you're first learning how to program, and honestly, for like most simple tasks that you're going to deal with, just getting something that works is good enough most of the time. Um, but computer science as a field kind of exists because we care about doing things fast, right? Or efficiently, with various definitions of what efficiency means. Uh, and so in this penultimate week of the course, what I want to start to care about is actually it's writing code that works still. We to be sure we want to keep doing that, but writing code that works efficiently. Um, and this will be the focus of most of your computer science degree if you choose to continue down this path that we've started on. Um, okay, but before we really dive into the contents of today's lecture, are there any questions about admin things, material from the last week, the quiz today, anything, any, any stuff like that? Okay, cool. All right. In that case, let's get started then. Um, so there's a couple famous canonical problems in computer science that come up over and over and over again, and that people over the last 50 years have thought practically to death. Like they've approached them from every single angle, there's like a wealth of literature around these problems and the challenges, the pitfalls, efficient solutions to them, problems with those solutions, and then solutions to those problems to those solutions. And maybe one of the most old school like OG problems is just the problem of I have some data that I want to store somewhere in some database or something, right? Some record keeping system, and I want to know whether or not I have already stored some key, right? In other words, I'm storing some data. You come to me, you say, hey, do you have this thing? Like you can kind of imagine I'm a librarian in this scenario. Like, hey, do you have this book? And I either tell you, yes, I have this book, or no, I do not have this book, right? This very basic record keeping task, simple as it is to state, already introduces some pretty interesting theory when you start thinking about how to actually solve this problem efficiently. And so this one problem is going to be the focus of today's lecture. And we're going to look at three different data structures, three different algorithmic approaches for solving this problem, each of them with their own advantages and disadvantages. And by the end of the lecture, you'll see a couple different ways of solving this problem. But perhaps more importantly than any one approach that you're going to see, you'll have an appreciation of the fact that in computer science, as in life, there are no one-size-fits-all solutions, right? Depending on the specific task you have at hand, you're gonna want to choose certain drawbacks over others, certain advantages over others. So with that, let's get started with the first kind of most naive approach to how you would solve this problem of I see a lot of data and I want to be able to search and look up whether or not I have a certain particular record in the collection that I've accumulated so far. Okay, so we're going to make a new file and we're going to call this list search.py. And in this first approach, well, actually, maybe let me pass the question on to you guys. So, or how about this? We'll flesh out the setup a little more, and then it'll be clear, a little more concrete what it is that I'm asking us to solve today. So we're going to represent some set of data that we want to store with just some random numbers for the purposes of today's lecture. So we're going to have a bunch of, we're going to use the random library, import random. And then I'm going to represent a ton of samples of numbers, right? Like maybe we'll have some, I don't know, for the purposes of this demonstration, we'll have a lower bound of 0 and an upper bound of 4, 5, 6, 7. I think that's 10 million, right? Assuming I've counted my zeros correctly. And then we'll have the number of elements that we're going to want to store be equal to the upper bound divided by 10, so a million. So what we're going to see today is I'm going to throw like yeah, a million random numbers between 0 and 10 million at you. And then I'm going to ask you, hey, is this number among the million that you've seen? This is going to be you can kind of see like the scale. This is kind of like you might think, oh, wow, million, 10 million, these are big numbers. But in modern practice, like in actual large scale applications that you see in industry, these are like peanuts, right? Like I think ChatGPT is like trained on billions, has like millions of nodes that's trained on like terabytes and terabytes of data. So these kind of big numbers are not unrealistic. Like I'm not just pulling this out of nowhere for the purpose of like this lecture specifically. So yeah. Okay, so now we're gonna have this. Let me ask you this. Let me ask you this. You're given a million random numbers to keep track of. How do you go about storing them in a way so that when I ask you, hey, do you have this number, you can tell me yes or no? Does anyone have any suggestions on like what we can do with the tools that we've seen so far in the course to kind of approach this? There's no wrong answer here, really. Um, yeah. Okay, yeah, we could do a set. A set would be one way of doing this, right? And a set in particular would work because, well, we don't really care about storing duplicate numbers, right? So a set is one way of going about this. Are there any other suggestions on how we could approach this? Yeah,
Range
a range.
would
So, no, say more.
it go from 0 to the last number?
0 to the last number.
That
Oh,
we would have all.
yeah. So to populate whatever data structure we're going to be using to store all our random numbers, we're probably going to use the range function. That's for sure. But now I'm talking about the actual structure itself, like the record keeping system.
Or even this.
Yeah,
Would
but
you really write all?
well, yeah, let's try it. That's going to be the first thing that we try today, actually, is, hey, let's just do it with a list and see what happens, right? So, okay, we're going to have some gigantic list, and we're just going to call it LST to start. And in the beginning, it's going to be empty. And what we're going to do is we're going to use range, as you suggested, to actually populate this. And we're going to say, okay, for I in range, the number of elements, right? These are the number of things that I want to put in my list. We're going to let sample be equal to random.randint something in my range of lower to upper, right? Some random number in this range. And then we're just going to say, okay, list.append the sample. Yeah? And so this is going to create this really, really big list with all these random numbers in them. And then if I want to check whether or not something is in this list, well, now what I can say is, here, let's break it up a little bit. We'll write, hey, we're populating the list. And then once we've finished this population phase, we can ask the user, I don't know, we could call it key is equal to input, enter a key to look up. And in fact, let's do this in a loop. Let's say while true, we can say enter a key to look up. Or, I don't know, Q to quit. something like this. And just as a way of like validating user input, we could say, okay, try this. And if this integer conversion fails, right, except a value error, because they entered Q instead of an int, then we'll break out of this loop. But okay, while they're inputting keys, we can actually now say, all right, we'll have a Boolean variable called contains key, and we'll just set it equal to is the key in the list, right? And then if it is the case that it contains, oh, here's what we can do. We can say print. And for the purpose of actually demonstrating the efficiency of these different things, we're going to time our code. And you might be wondering, well, how do we do that? It turns out there's this nifty Python module, very creatively called time, that provides you with functionality for evaluating the runtime of your code. So let's see how to do that. We're going to import the time module. And then to actually evaluate this operation, right? This is the lookup of our key. We'll do this. We'll say the start time is equal to time dot perf counter. This is just this function in the time module that we're going to use. And you can kind of think of this as like setting a stopwatch. It just records whatever the current system time is. And then the end time is going to be equal to, we're going to use the same method again. So now we're saying, okay, get what the current time is now. And then we can print what the actual runtime of our code was by saying print. Oh, and here's another thing we could do. We could say, depending on whether or not the key was found, we could write string found. Well, let's have two different cases for this, actually. We'll say if contains key, right? So if we found the key, then we can write, okay, hey, well, in either case, we're going to say the runtime was equal to the end time minus the start time. So we'll start with that. And then if we found the key, we're going to print key found in runtime, right? And then we're just going to print what our runtime was. And there's a little nifty thing that you can do with format strings that I haven't shown you yet, which is that inside the format string, you can specify how you want your floats to appear. And so if we want to get our runtime to a certain number of decimal places, you can do that by writing colon after the variable name that you want to drop into your string, and then dot 6f. And this just means include this like 6 decimal places in this float value runtime that you're going to see here. And otherwise, if the key wasn't found, so our list doesn't contain the key, then we'll just print key not found in the same thing, right? Runtime dot 6f. Okay. There we go. All right, so we have some code here for profiling the search operation with our list structure now. Let's see what happens when we actually run this. So in a new window here that I'll just generate like this, terminal. What we're going to do now is say, all right, let's try running this. Python 3 list search dot py. Oh, okay. What have I forgotten here? On line 12, I forgot a colon. Classic. There we go. Any other syntax errors? Nope. Okay, it's populating the list. You can see it's taking a while because it's a big list. Oh, I don't like the way I formatted this. Let's fix this so that we do it a little more aesthetically. Give them a little space there. Okay, so we'll quit. Oh, it says value error not defined, and that's because I put 3 R's. There we go. Alrighty. All right, so we're populating the list now. Again, it takes a little minute. All right, so we have 10, or we have 1 million random numbers between 0 and 10 million in this list now. Let's see if one of them is 7. Okay, so it looked up whether or not 7 was contained within the list, and it took about 0.07 seconds. You might be thinking, whoa, hey, that's pretty fast, right? Um, but this is actually really slow on the scale of like uh, massive numbers. And the reason why, let me see if I can explain why this is slow. You have to think about it a little algorithmically here. So what's actually going on is when I have this, let me see how I can illustrate this. So if I have a bunch of numbers, we'll just show it in the terminal, right? Like 6, 2, 7, 1, 0, 4. Like imagine these are just, this is the first part of all the random numbers that I generate. Then in order to, what this in operation actually hides how the key is being looked up in our list. What's happening under the hood is Python needs to search through the entire list from start to finish, one element at a time, to determine whether or not some key is contained among the numbers that we've seen so far. And you may think to yourself, well, this is unavoidable. How else would I do this? Of course, I have to check everything in my list, right? And it turns out there's a way that we can be a little more clever about this. Um, so I'm going to illustrate this on the board. Because the moment you start talking about theory, the chalk comes out. So what if instead of just kind of storing our numbers randomly, here's a more clever way we might do this, right? Like here's the first approach we had where we were just kind of, I don't know, doing whatever the heck, 100 maybe, and then so on. And we had to linearly go through this entire list anytime we wanted to look something up. Well, if these numbers were sorted, we could actually do this a little more efficiently, right? Like what if I guaranteed you that all the numbers that I'm giving you in your list are sorted? Then it might look something like this, right? Then we might have the smallest number is like 0, and then 2, and then maybe 6 with like a different list. It's not the same as this one. Or actually, yeah, let's make the same. Right? 2, 4, 6, 7, 9, right? And some more stuff. And if we imagine for a second that this is just all the things in my list, right? Then to look up whether or not something is in this sorted list, I don't actually need to linearly go left to right, right? Like, let's say I want to check if there's some key 5, right? My key is 5. And I want to check whether or not it's contained within this list here. Then I can just say, okay, go to some element in the middle of my list, like 4, right? And compare 4 to 5. Yeah? If the key is less than 4, then I know that if it's contained within my list, it has to be in this first half of the list because it's sorted, right? And so I don't have to care about any of the stuff in the second half of the list anymore. In other words, I have shrunken my search space to 1/2 of what I was originally considering. Yeah. And then, if I can repeat that process, I can say, okay, now compare my key to the thing in the middle of this list. In other words, let's say the key was 3 here. And I say, okay, compare the key to 2. If it's greater than 2, then I only have to, greater than or equal to 2, then I only have to care about things in this section of the list here. And I can discard everything to the list. or everything to the left of 2, right? So at every single step, we're cutting out half of all the things in the list without ever needing to explicitly make any comparisons to them. So the number of comparisons that I make here in order to determine that 3, right? And then I can check, okay, well, now I look here and I say, is 3 contained within my list in this tiny little thing that I did here? And I can say, no, it's not, right? And it's missing, and therefore I would say that it's not found. So whereas here we had to make 1, 2, 3, 4, 5. Well, and then maybe 9 was like here or something like this. 6 comparisons. In other words, we had to make one comparison with everything in the list when it wasn't sorted. To determine that the key wasn't contained in this list, we only had to make 3. And the actual number of comparisons, if the convention in computer science is we let n, the number n, represent the size or the number of elements in whatever data structure I'm working with, right? In order the size of my search space, potentially. So with an unordered list, the search takes or like roughly n time, right? Because I need to do n comparisons here. But when it's sorted, my runtime of my search actually just becomes log base 2 of n, which is, and the reason why it's log base 2, I don't know if you remember from a couple quizzes ago, the intuition here was that log base 2 is kind of the number of times you need to divide something by 2 in order to end up at 1. So this exactly captures the number of comparisons that I have to make when I have the guarantee that the list is sorted, right? And these numbers, n versus log of n, they scale very, very differently, right? When n is like, I don't know, 10 to the 24, log 2n is only like 8, I think, or something, right? So this number grows much, much, much more slowly than this number does. And it allows way faster lookups, okay? And I've been talking theoretically about this advantage, right? But what we're going to do next is we're going to implement a new structure for storing these numbers that takes advantage of keeping them in a sorted way in order to like speed up lookups. And we're going to observe in practice that it's actually way, way faster. All right? Any questions about this? Yeah.
I mean, just like the program say it was not found.
Yes.
But like, so it didn't work.
Oh yeah, it worked. It just 7 wasn't in there, right? Like we could keep checking because these are random numbers, right? Like there are a million numbers in my list, but I'm drawing from a pool of 10 million numbers. No, every single number in the list is a random number from like 0 up to 10 million, basically. Yeah. Any other questions? Okay, so let's see how to do this other more efficient structure now. All right, so we're going to quit this. And now I'm going to make what I'll do is I'll copy this list search into a new file that I'll call binary tree search.py. And then we'll open that up. And so we're going to follow roughly the same. Oh, actually, and before, we'll just do this. So instead of doing a list here now, we're going to get rid of this, right? Forget about all this for now. And we're going to make a new data structure for storing all this stuff called a binary tree. And this is one of the most basic data structures you're likely to encounter in computer science. So let's see how it works. So instead of storing everything in a list, the way that we're doing here, the intuition of a binary tree is, so if this is the same sequence of numbers as before, right? If maybe these are the numbers that I want to see, then a binary tree works like this. the first number that you get, 6, it's going to store at the top of the tree for the root. And then the next number that it sees, well, if it's less than the current node, we'll store it to the left, call it the left child of this node. And if it's greater than the current node, we'll store it to the right. So, okay, 4, that goes here, right? And now, okay, the next thing is 7. So 7, we compare it to 6. It's bigger. There's no right child yet. So it becomes the right child, 7. Yeah? Okay, the next thing is 0. Where is 0 going to go next? Anyone have any suggestions on where 0 is going to go in this binary tree? You can see it, and like the tree is starting to flesh out, right? Like we're storing things in nodes now. You can kind of think of these as like nodes in this tree. Where's 0 going to go? Yeah?
It would be like left of 4.
Exactly, right? Because the way it's going to go about this is it's going to say, okay, compare 0 to 6. It's less than 6. Go to the left child. Now, compare 0 to 4. It's less than 4. So it becomes the left child here, right? Okay, where's 100 going to go? I feel like you know the answer, but we're hesitant to say it, yeah?
The right of 7.
Exactly, the right of 7. Same thing, right? Compare to 6. Well, it's bigger than 6. Compare to 7, it's bigger than 7. There's nothing here yet, so add a new child, 100. And the last one's 9. Where's 9 going to go? It's less clear maybe, right? Yeah?
The left of 100.
To the left of 100, exactly right. So it's bigger than this, it's bigger than this, but it's smaller than this. So it goes here at 9, right? And if I really, and so why is this a smarter way of storing things than just in a linear list like this? It's because if I want to look up where like 100 is, in other words, if I want to say, is 100 in my list, then instead of doing 1, 2, 3, 4, 5 comparisons and traversing things linearly, I only have to do 1, 2, 3. In other words, we've exploited the sorted structure of the tree to look things up faster. Yeah? So now let's actually make this. So we're going to make a new class called a binary tree node. Okay, like any class, we're going to have an init method, right? So we're going to say init, and it's going to look something like this. It's going to take self, like any class, or any method of a class. And it's going to have a value and a left child, which will be none by default, and a right child, which will be none by default. Okay? And now we're going to store these things. We're going to say, okay, self.value is equal to the value. Self.left is equal to left. Self.right is equal to right. Yeah? Okay. So we need to be able to insert things into this tree, right? The same way that we were able to insert things into our lists with append. So we're going to make a method now called insert. And each of these, you can kind of think of each of these node objects as representing one node in the tree. And so what this left thing is actually going to be is going to be another node object that's the left child of the current node. And the right here will be the node object that's the right child of the current node. Okay? So let's make a method called insert now. And this will be a new value that I want to insert into my tree. And what we're going to do is we're going to say, okay, we're going to implement exactly the operation that I described before when I was asking you how to insert things, right? So we're going to say, um, if this, well, we could call it new value, I guess, to be like really explicit. So if the new value is less than self.value, then we want to do what we want to do is insert it somewhere in the left tree, right? And so we're just going to pass that responsibility. Well, first we have to check, are we at the bottom of the tree, right? In other words, is that child none? Because in that case, I just need to make a new node object as we did before and set its value equal to the new value, right? So let's check if the self.left is equal to none, or another way of saying this, we would use 2 here. We could just say, if it is none, in other words, it hasn't been created yet, then what we're going to do is make a new node object and get it and assign its value to be the new value. Yeah? So we're going to say, okay, then self.left is now equal to a binary tree node whose value is the new value, right? And whose children should be none, right? Because it's the bottom of the tree. So these default values are okay in this case. Otherwise, if it's not none, then we're going to do this. We're going to say, okay, then there's already a child there, right? Like this would be the case where I had to insert 5, right? Like let's say I'm adding a new value 5. I say, okay, I compare it to here. Well, it's less than that, right? Which means that I need to insert it somewhere in this subtree. I don't really have to care too much about where, though. I'm just going to pass that responsibility down to this node here and say, you handle the insertion. Okay, this is an example of what's called recursion in computer science. It's another very powerful concept that you'll likely explore more in a future course. So you'll see come up in future courses that you take. So we're going to say, okay, then self.left dot insert what the new value is. I say, you take care of it. You handle the insertion. And then when I call insert on this guy 4, what it's going to do is it's going to say, okay, 5 is bigger than 4, and it's going to do the new node creation for me, right? Yeah. Okay, so this was the case where new value was less than the value of the current node. But there's another case, right? It could be greater than or equal to the value of the current node. And in this case, we want to add it to the right. So we're going to do the same thing, but just mirrored, right? We're going to say if self.right is a none, then make a new node. New value. Otherwise, have that guy, handle the insertion. What the new value is. Okay? And so that's what our insert method looks like. Any questions about how insert works? Yes.
What, because something, is that even more of a computing? Because then we're having process maybe like double the amount, so let's say every number is turned twice.
Yeah. So for this specific example, where we're only interested in storing the key, it wouldn't really make too much sense to store duplicates. But sometimes you want your key and the actual value to be different. And in those cases, well, I suppose it still wouldn't make too much sense there. Yeah, if you have a duplicate element, then I guess what you could do is you could just do nothing, right? In the case where, like we could write it this way. We could say, okay, else if the new value is greater than self.value, do this. Else, right? In this case where they're equal, pass, do nothing, right? Because it's already there. I don't have to insert it a second time. This is another way you could write this, right? Okay. So yeah, thanks for bringing that up. This is our insert method. This is what it looks like. Any questions? Any more questions about it? Okay, so we handled insertion. Now we actually have to be able to look things up too. So we're going to have another method that we're going to call search and some value. And how's this going to work? Well, it's going to look very similar to insert in the way that we kind of recurse down the tree. So yeah, let's see what that looks like. So the first thing that here's what we're going to do. We're going to say if the value is less than self.value, then if my value exists, it's somewhere in the left subtree, right? So call search on that. Of course, the only situation in which this may not work, there are two cases here, right? The left child could be none, in which case our key is not contained in our tree, or there could be a node there, in which case we need to search the subtree rooted at that node, right? So to illustrate the difference between these two cases, this would be like if I had some like value -1 that I wanted to add to my tree, then I would say, okay, -1 is less than this, so I have to search within this subtree. And this is defined, right? And say, okay, then we have this node call its search method, and it says, okay, -1 is less than this. I see there's a left node here, so I'm going to have this guy do this. I'm going to call this guy's search method now. And then we say, okay, -1 is less than 0, but there is no left child here, right? Left of this node is none, so we're done. We return that we haven't found the key in this case, okay? So this is going to search is going to return a Boolean value, like true or false, depending on whether or not it finds the key. So if self.left is none, then return false. We're done. Else, we're just going to return self.left.search with whatever the value is. And then we're going to handle the symmetric case where, okay, if value is greater than self.value, okay, we'll check again. Is self.right none? In this case, return false. We know for sure that it's not in our tree. Otherwise, return self.right.search the value. Oh, and this should be else if, elif. And then there's one more case, right, where they're equal again. And if they're equal, it means we found the value, right? So we should return true. And this is how our search works. There you have it, a full-fledged binary tree encoded one node at a time. So this is what it looks like. Now let's actually see how it performs, right? So instead of populating a list here now, we're going to say, okay, we're populating the tree. And here's how we'll go about it. We'll say the root of the tree is equal to the first random sample that you give me. So we'll say binary tree node, a new binary tree node, where the value is the first sample. So random.randint lower upper. There we go. Okay. And now for every single one of these things in I-1 or num-lms -1, because we've already inserted one of the things, we're just going to say, okay, sample is equal to a random integer. And then instead of saying list.append sample, we're just going to say root.insert whatever the sample is. Okay. And it'll be interesting to see, well, no, actually, we'll handle that in a second. And then we're just gonna, like, the rest of our loop is gonna look very similar to the way that it did before. So we're gonna enter a key to look up or Q to quit. And we're gonna time it again. But instead of doing this key in list operation, we're just gonna say, okay, root.search, whatever the key is. And then we'll compute the runtime the same way that we did before. So let's see how this compares to, I want you guys to remember this. The lookup operations that we were doing with a list were roughly on the order of like 10 to the minus 2, right? There's like 2 decimal places, and then we had a number here. So about 10 to the minus 2 seconds for lookups in our list. But now let's see what they are for our binary search tree. So let's try this now. Binary tree search.py. Okay, what have I done? 23, go. Classic. One of these days. There we are. All right, so it's populating the tree. You'll notice, well, I won't make any mention of that now, but we'll see in a second. 10 million numbers, or a million numbers. It's taking its sweet time, though. Ah, okay, we're good. It's populated the tree. Now, let's try looking up a number. We looked up 7 before. Let's try that again. Whoa! Okay, before we were getting lookup times of like 0.07, and now we're at like 1,000 times faster than that. This is like 0.000032 seconds, right? You can see it was so much faster than the lookup operation that we were doing before because it only had to do roughly log n comparison operations instead of the roughly n operations that it had to do in the case of a list. So this is a way, way faster, smarter way of searching for things and storing them than the list thing that we had before. For searching, it's faster. Any questions about the binary search tree, the binary tree? Yeah.
10,000 values, right? Range of 1 to 1 million. Like I was just wondering how do we know that we populated it right if it always says keep on. Like we run it again, it's gonna see at some point keep on.
Yeah, I mean, there's a 1 in 10 chance that it, like, we can just keep going until it finds something, right? Like 8, okay, didn't find that. 10, how about this? 11, 12. Oh, there we go. It found 12. That's in there. Yeah, it's like roughly on the same order still. Yeah.
So it is the case though that like for certain numbers, they will be sort of like unfairly, especially if they're like nearly 10, right? That they'll be sort of like unfairly so much longer to take to the process to find compared to other numbers. Will that still be like, will that be an issue anyway, like when it's like really large scale things, or do we not to use this so much?
Oh, sorry. So let me see if I understood your question correctly. You're saying that for really, really big numbers, there's a,
Yeah, sorry. No, for like, for example, for the one you have behind you with like 9, like if it had kept going, right, and there was just more numbers to this list, right, and later on in the list, at a certain point, you have to go to 6, 7, 100 to 9, or something. Whereas like a number like 0, it's very easy to get to. It's the 6, 4, 0. That's like a huge difference, right?
yeah, so this is a fantastic question. There's this really, we've made an implicit assumption about the distribution of the numbers and they're uniform, right? They're uniformly generated, uniformly randomly generated. So as we keep adding numbers to this tree, the assumption is that it should be like roughly balanced. Like you're never going to end up with one super duper long path, right? But that could happen, right? In the worst case, we could add 101 and then 102 and then 103. And every time you would end up with something that looks like a list again, right? Because you're not actually ever taking advantage of the fact that you have two children, you know? And so this is what we call an unbalanced search tree. And there's a way of fixing that. You can modify this binary tree data structure that we've written so far so that it self-balances. In other words, it's aware of when one of its like little child paths is too long, and it can kind of efficiently reconfigure itself by shifting nodes around in such a way that it becomes balanced again. So there are other data, like really cool data structures that handle this sort of thing. Yeah, but it's a good question. It's another thing to be aware of for sure. It's like what happens in the worst case rather than the average case of these insertion operations. Any other questions? Yes.
Well, maybe you're gonna get to that, but it seems like we have to wait quite a while until it actually.
Oh, you guys are on fire with the good questions. Yeah. Sorry, was there something else you wanted to add?
The original services technically still show it because of account for the making of the tree being longer.
Yes. So let's make this more concrete. So far we're only timing our insertions, right? But now let's profile the actual creation of the data structures themselves. So we can do that the same way that we did before. We can say, okay, start time is equal to time dot performance counter here. And then after this population, we'll say end time is equal to time dot performance counter over here. And now we can print the tree populated in end time minus start time. Dot F here, 6 seconds. So this will actually record how long it took to populate the tree. And we can actually make a similar modification. Well, so let's see how this fares now. Quit. So we're going to run this. And while this is running, I'll make a similar modification to our list search. Say, okay, here's where we'll throw this in here for it to be a fair comparison. Say, okay, start time, performance counter. Okay, so it finished running over here. It took about 22 seconds to populate this, right? So let's see how the list does. End time is equal to time dot performance counter. And then same thing as before, we can now print list populated in end time minus start time. Dot 6 seconds. Okay. Now if we let's see how our list search fares now to populate with the same number of elements. Wow, okay, so it created that list, or the data structure was created significantly faster than in the case of the binary search tree, right? And so this is why this is like an excellent illustration of what I said at the start of lecture, which was that in computer science, as in life, there is no one universal best solution. If you care more about fast searches, you want to use a binary tree. But if you care more about fast insertions, then the list clearly wins out. But why does the list win out? It's because when you want to add a new element or insert a new element to the binary tree, you have to do roughly log n comparisons. It's like the search, right? You need to walk down this tree. But internally, if we were to write this list ourselves, the way that Python handles it is it always remembers where the end of the list is. So when you do list.append, it just tacks the thing onto the end of the list. It doesn't have to do any comparisons at all. In other words, we would say that this operation takes constant time. It doesn't depend at all on the size of the list. It always just takes like a single operation, basically. And so you can see that you can clearly see that difference reflected in the difference of these runtimes, right? Like inserting in a list is way faster than inserting in a binary tree. So yeah, great question. Anything else about this? Any other thoughts, suggestions, questions? Okay, cool. In that case, I promised you 3 approaches to this problem. We're going to look at one more. So we've seen how to do it with a list. We've seen how to do it with a binary tree. The last approach that we're going to look at is something called a hash table. And let me illustrate again the theory of how a hash table works. Or, before we actually get into writing the thing. So the way a hash table works is that it stores things in what are called buckets. And you can think of buckets as this like table, basically, right? Of like all these elements here. And it has one bucket. Each of these is a bucket. Or a bunch of different buckets in the table. And so when you give a hash table 6, and what it does is it puts 6 through this thing called a hash function, and then it spits out some address in the table, some bucket in the table where it should put 6. So maybe, I don't know, and I haven't told you specifically how exactly this hash function works yet, but we'll get to that in a second. So it's going to throw 6 like here, maybe, right? Maybe that's how the hash table works. And then you give it 4, you feed it into the hash function does some magic, and then it puts it here, okay? And then you give it 7, and it puts it here, right? This is just an example of how this hash function might work. When you then search for something in a hash table, it uses the same hash function again to say, wait, which bucket did I put this in again? And so it computes the hash of the thing you want to look up, like 6 in this case, and it checks that bucket. And if 6 is there, it can tell you that 6 is there and return true. And hash tables are really, really cool because the insertion time is like that of a list, right? It's like immediate. In other words, it's constant in the sense that it doesn't depend on the number of elements that you're adding to the list, right? Like it can always compute this in constant time. But like a binary tree, the lookup is also really fast, right? In fact, it's even faster than a binary tree. It's also constant because it's using the same hash function into the table, right? And so it has constant insertion time, constant search time. You're like, wow, why did I even talk about lists and binary trees at all in the start of this lecture if this really cool thing exists? And it's because it comes with other drawbacks that we will see a little bit later. But okay, there's one important detail which I've glossed over in this description of a hash table, and that's how does this hash function actually work? Well, there's a couple different ways of implementing hash functions, but the expectation, what we want out of a hash function, is that it should take a number, right, or something that I want to insert into the table, and spit out a bucket, and those buckets should differ a bunch depending on the key that you feed into it, right? Like I never want to have a hash function that sends, or I don't want to have a hash function that sends 6 and 4 to the same thing, right? That would be bad. I want to make sure that this hash function spreads my keys out nicely over the table for this thing to work, right? And so it turns out a very simple hash function for doing this, sometimes used in practice, is just our good old friend, the modulo operator. So one hash function, in particular the hash function that we're going to implement for the hash table that we build, is it's just going to take the key, the new value that you want to insert, mod the size of the table, so the number of buckets. And it turns out this is actually a pretty good hash function, right? Because if you have something like 100, and I don't know, there's like 1, 2, 3, 4, 5, let's say 6, okay, for the purpose of this simple table, then what this would compute is it would say, okay, 100 mod 6, I don't know, what would that be? It would be 4, right? Because 96 is the closest multiple of 6, and then there's like 4 after that. So it would say, okay, 100 mod 6 is 4. So go to 0, 1, 2, 3, 4 and insert it here, right? That's how this hash function would work. And it turns out this does a pretty good job of spreading the numbers. It's very, very simple. So this is the hash function that we're going to use. Okay, let's make this now. So again, we're just going to do a very similar thing to what we did before. So we're going to copy list search into a new file that I'm going to call hash table search.py. We'll open that up. And so, okay, we're going to make a new class now. Whoa. 8 go. Called hash table. All right. So what are we going to do here? Well, we're going to have an init method as before. And when we set up a hash table, one thing that I'm going to want to do is specify optionally the number of buckets to have in my hash table. Okay, this is going to be one of the arguments to this hash table. So we're going to say the number, we can say like init buckets. It's going to be self init buckets. And by default, we'll just set this to 100. Okay. Okay. And then internally, we're going to store this table as a list. Right. So we're going to say, I want a list of size the number of buckets that the user has possibly specified. So we'll say, okay, then self.buckets, this will be the name of our table, is equal to, and here's like a quick shorthand way of initializing an empty list with a certain number of elements. You could just say, okay, it's none, the list containing none, times init buckets. So the list class has overloaded this times operator to just be like duplication, sort of. It's saying create init buckets many lists that only contain a single thing and concatenate them all together. Right? That's kind of what's going on in the hood, under the hood here. So, okay, we have this big empty list now. So we're going to want to write an insert method as we did before. And we're going to have a new value to insert. And it's going to look pretty simple right now compared to what we did for our binary tree. We're going to say, okay, compute the hash. So we'll just say the hash value is going to be equal to the new value mod the length of self.buckets. Right? This is the hash function that I was describing just now. And then what we'll say is, okay, self.buckets at that hash value, right? Because that gives you the index, is equal to the new value. And that's it. That's what our insert looks like. Okay. All right. So what does our search look like? Very, very similar. So we'll say hash value, same thing, is equal to new value, mod the length self.buckets. And then we'll just return is the thing at the address of the hash value, self.buckets. Is this equal to, oh, sorry, this should just be value here. Is that equal to value? There we go. That's our hash table. Looking pretty easy, right? Okay. Let's see how it does performance-wise. So this is what the setup will look like. We'll just say, okay, our table is going to be equal to a new hash table. And as the argument, we'll say it's the number of elements, right? That's roughly how many things I'm going to stick in here. And then we'll say table dot insert the sample. And the table will be populated, and this time, and then I'll fix it here too. Delete. Populating table, hash table, I guess. And this isn't going to change. None of this here is going to change, right? This is going to look exactly the way, oh, well, actually, this will change. It's going to be equal to table.search, the key. Okay, now let's see how this does. I've promised you many amazing things about hash tables. Let's see if they will deliver. All right, so Python 3, hash table search.py, populating the table, doing its thing. Okay, wow, that was pretty fast, right? Like roughly on the order of our list again. A little bit slower because we had to compute the modulo operator for each of them, but definitely way faster than the 22 seconds that it took for our tree, right? Now let's see how it fares on insertions or on lookups. So we're going to say, I don't know, lookup 7. Wow, okay, it's like rough. It's surprisingly similar to the performance of the hash table, right? And so it seems that we've achieved the best of both worlds. We have fast insertions and fast lookups. So where's the problem? Does anyone see what the problem might be, out of curiosity, with this thing? Well, there's one problem. I'll give you this as a hint. There's one problem that doesn't even have to do with performance. In fact, it's like a correctness problem. There's something wrong with the hash table that we've just made, right? Something breaks. I'm curious if, like, from the description that I've given so far, anyone can see what it is, maybe. Yeah?
I mean, I don't know what it is, but I just use the module, but by the way we treat the values, like
Yeah. So you're on the right track here. Okay, to illustrate this, we're gonna work with like a simple example of a hash table. And to do that, I'm just gonna add this here. If name is equal to main. And I'm just adding this code so that I can import this class, this module, and work with hash tables without everything actually running. So don't worry too much about what I'm doing here. It's okay if you don't understand it. Go here. That did not work. Oh, there we go. It did. Cool. All right. So quit. So we're gonna, in just this simple interactive shell, we're gonna import this hash table thing that we've just written here. So we're gonna say from hash table search import our hash table. And now I'm gonna just make, I don't know, like a new simple, silly little hash table with only 10 things in it. So I'll call it T is equal to a new hash table with 10 buckets. Okay. As you can see, T is like this hash table object. And then what I'll do is I'll say, all right, T, I don't know, let's insert 7. So what happens under the hood here is the hash function is 7 mod 10, which is just 7. So it's a little better here. 10 buckets. Oops. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And you probably can't see the stuff at the bottom. That's okay. We're not going to go down there. So, okay, it says the hash address is 0, 1, 2, 3, 4, 5, 6, 7. So it puts 7 here in my hash table, right? Okay. Let's try inserting. Oh, and we can check now. Hey, is this item in my hash table? Yeah, true. It's in there, right? It just added it. Good. And we can, as a sanity test, say, okay, well, is 6 in there? No, because you haven't added it yet, right? But let's see. Okay, we can insert other things too, like 8. And we'll see it behaves as we expect it to. It says true. But now let's try inserting 17. Okay, so we've inserted 17. Is 17 in there? Yeah, duh, you just put it in there. Is 8 still in there from when we added it earlier? Yeah, 8 is still in there. Is 7 still in there? No. 7 is gone. What happened to 7? I'm curious if does anyone have an idea of why it's not in my, yeah? Yes, we overwrote it because 17 mod the number of buckets is the same as 7 mod the number of buckets. So it went into this table and it got rid of 7 and it put 17 there. This is terrible. Our data structure overwrites things that we've already added to it. It doesn't even work. It might be fast, but it's not actually working yet. So what do we do? What do we do to fix this? Does anyone have any ideas on? Yeah?
Yeah, mom.
Oh yeah, so we could like change the number of buckets, right? And maybe that would send 7 and 17 to different places. But there's always going to be 2 elements, no matter what bucket size you choose, that collide, that map to the same bucket. And we need to handle these collisions. Yeah.
Instead of putting like the position of you append this.
Yes. This is one way of fixing this. And this is called chaining, right? Instead of just having a single value in each of these buckets, we actually have a list of values. And instead of just like overwriting what's ever there, we look at the list at that position. And if there's something already there, then we append it to that list, right? So this is one approach to resolving collisions in hash tables called chaining. There are other ways of resolving collisions. One of them is called open addressing. And the way that that works is, okay, let's say I have 7 here and I want to write 17. I check when I compute this hash, is there something already there? And if the answer is yes, I try a different bucket. And there's one technique in open addressing called linear probing that just keeps trying the next bucket until it finds the next open one. And then it just throws 17 there, right? Like maybe there's some other stuff in these things. So this is another technique of resolving collisions in hash tables. And much like, deciding between different data structures to handle this problem of looking up things, there are different trade-offs for each of these approaches to handling collisions. There's advantages and disadvantages to chaining versus probing, right? And so hopefully in today's lecture, I've given you some appreciation of like just how clever you can be and how many intricacies start to arise for a very, very simple problem of just storing things and looking them up. And this is just one type of problem, right? Like next lecture, we're going to look at sorting, which is a totally different kind of algorithmic problem with a bunch of its own solutions and each of their advantages and disadvantages and really clever, beautiful ideas of making things efficient. Yeah. And so we could, in the last 10 minutes of class, we could implement this chaining, and it would be a very simple modification to this hash table. We would just start adding, we would replace each of these with lists and then do insertions instead. But in the last 10 minutes before the quiz, I also kind of want to give people a chance to ask any final questions and maybe take a little breather before we launch right into it. So actually, maybe that's a good exercise, huh? For the homework. It's implementing chaining and probing. Yeah, that's good. I might do that. Okay, cool. Yeah, but are there any questions about anything we've seen today so far? Anything? Cool. In that case, feel free to come and ask me questions about anything, about the material or whatever. We're going to take a little 10-minute break now. Free to go to the bathroom, whatever, breathe. And then at 11:55, we'll start the quiz. Cool. Yeah, let me just quickly end the meeting here.